Good, good morning, members. I'm going to discuss about stereoisomerism, and let me start straight away. In stereoisomerism, we are going to look at compounds whose molecules have the same atoms bonded to each other, but the only difference is how they are arranged in space, what may call spatial arrangement. Stereoisomerism is divided into two. We have C trans isomerism, or what you may call geometrical isomerism, and then optical isomerism. With the geometrical isomerism, here as the word is geometrical, as you hear the word geometrical mathematically, we are going to look at planes, how how these atoms or how the structures of these compounds appear in terms of their atoms and bonds in 3D. Let me use 3 dimensions because most all of these are in 3 dimensions. They are figures if you are to draw them. But in simple terms, this is where isomers have the same structure formula but differ in spatial arrangement. So the structure formula is the same, but what differs is how the atoms or group of atoms are arranged in space. That's what I mean, but across a double bond. So actually, geometrical stereoisomerism is explained better with alkenes because for them they undergo that geometrical. That is because we're having arrangement of these atoms across the double bond, and it is alkenes with it. So this kind of isomerism is found in them. Yeah. So, but I want you to quote these two terms, cis and trans. Where is trans? Yes, and trans down here. So cis means the atoms which resemble, they lie on the same side. Now, before I go there, I would like to explain why we are having this type of isomerism in alkenes. If we have a single carbon-to-carbon bond, this one allows for rotation of atoms which are bonded to these carbon atoms with a single carbon-to-carbon. Even the structure itself can freely rotate. But provided there is an additional bond we call a pi bond, like in alkenes, this one restricts rotation, free rotation. So these carbons cannot freely rotate around, cannot freely rotate. So there is restricted rotation, and that's why it is adopted in unsaturated organic compounds like alkenes. Also, the other thing uh, is the groups. Now, the atoms which bring about this isomerism is true if the atoms are attached. Those two groups of atoms attached on these two adjacent carbons should be should not be of the same kind. They should be of different kind for this geometrical stereoisomerism to come about. If they are of the same kind, then we cannot have that. Let's say in ethene, where this side we have a hydrogen, even on this side hydrogen, then that one cannot have cis and trans isomers. It should be possible only if on each carbon there are different atoms, a group of atoms. Hope I've cleared that. So geometrical isomers can be, this one is N, you will clarify, you will change that in your notes. This is N, can therefore be one cis geometrical isomers. These are isomers where identical groups of atoms, Ig methyl group, are on the same side of the double bond. Then trans, of course, they lie on opposite sides. So the central atom, I beg your pardon, the two carbon atoms with the double bond, I've said clearly they should have different atoms on them, such that Let's say on one carbon, if there is a hydrogen, there has to be a methyl group CH3, but not hydrogen. Then these isomers will not be possible. So the other thing, because there is a difference in arrangement of atoms across the double bond, the physical properties of these isomers are different, and some of them may differ slightly with their chemical properties, e.g., different rate for the same reaction. So we mean the chemical reactions may not differ completely, but let's say the rate at which they occur may change. So I'm going to use examples here. We have but2-ene. I hope you remember the formula for but2-ene. It is a CH3, CH double bond, CH, CH3. That's how we write it. Now but2-ene, because you can see now the carbons with the double bond are there. They have a hydrogen atom attached and the CH3, as you are going to see down here briefly. So this one has two isomers which are illustrated below. The geometry of the molecules is different, how the atoms are arranged across. So the isomer with both CH3 groups on the same side of the double bond is called a cis, and that with the on opposite sides we call it a trans. So the word trans means across. So they are across each other. If you remember matching in nursery, they are across. So they are here actually. So the cis but2-ene, the CH3 are on the same side across of the double bond between these two carbon atoms. Then the trans, you can see they are across. One CH3 is on one carbon on the other side, another one is on the other carbon on the opposite side. So it qualifies to be a trans but2-ene when you are naming. Another example is 1,2-dibromoethene. Now these haloalkenes are formed from alkynes. When you react an alkyne with a halogen, yes, in presence of a halogen carrier, we can form them. So it means here the triple bond, the second pi bond was the one which was substituted by bromine atoms in a reaction we call substitution reaction to form, because this is carbon 1 and this is 2, it means the atoms were added to carbon 1 and 2. That's what 1, 2 means. Then di, because they are 2, we use di. Then bromo is a prefix for bromine atoms presence. So ethene, because there is still a double bond. Now because the bromine atoms are on the same side across the double bond, it is called a cis 1,2-dibromo. Then this one, because they are across each other or diagonal to each other, we call it a trans 1,2. So the same example here, it is also haloalkane, but chlorine atoms. So the idea is the same in naming. Then butene 1,4-dioic acid. Here we're having two carboxylic groups. That's why you see dioic, and they lie on carbon 1 and 4. If you follow nomenclature 1, 2, 3, 4, on 1 and 4. Then because the carboxylic is more senior, that's why the name is ending. So butane 1,4-dioic acid. So there is no way we can remove, I explained last time, there is no way we can make the double bond less, because it is less senior to carboxylic. It remains in the name butene, but when you are naming, we have to state the position of the carboxylic group, then we end with the oic. So the one where the carboxylic groups are across each other, it is a trans butene 1,4-dioic, and where they lie on the same side, it is a cis butene 1,4-dioic acid. So I've explained the word the trans means across. Then when you go to optical isomerism, so this kind of isomerism is specifically talking about how these molecules with the same structure formula or molecular formula have difference in how they rotate plain polarized light. So polarized light, to briefly talk about it, when we know light general as white light, it is actually like the mother of these other forms of light. So white light, you know very well, it is made up of many different components. If you remember the colors of a rainbow, red, orange, green, yellow, indigo, violet, blue, so those ones, and they form white light. Now that light is the normal light, because if you pass it through a material which can reflect bend light, it is going to be split into different components. In other words, different components are going to take on different directions, and that's how normal light should do. But with the plain polarized light, meaning light of only one color, so like red light, green light, blue light, those are polarized lights. So they are made of only one. So if you pass them through a refracting material, it will take on one direction because it is only alone. So that is polarized, I mean here. So in terms of our isomerism, if you have such a compounds which can which can rotate through such light differently, we say they are optically isomeric. So let me read this text. If a molecule contains a carbon atom, but how do they come about? There has to be a carbon atom which is surrounded by four other different atoms or group of atoms. And in such a case, uh, let me illustrate what I mean. So for it to be possible, there has to be groups of atoms or atoms. Let me call atom A, atom B, then we have our carbon, then I have atom C and atom D. So if we have such compounds with a central atom surrounded by four other atoms or group of atoms, then such a compound can form optical isomers. Now this central atom is called the chiral atom, CHIRAL, chiral. Then the general formula of those compounds which are showing optical isomerism, we can call them optical isomers, or they are called enantiomers.